It's Paul again, this time with the script showing you lots of illustrations of manifolds in R2. These are easy to graph and they illustrate most of the important ideas. I'm going to need to evaluate some derivatives, and I'm also going to want to draw a couple of circles. I'll maximize my real estate. And now let's work on the simplest imaginable example, the unit circle. If you understand three different ways of getting the unit circle as a manifold, you have basically captured the basic ideas of this subject. So I'll make an empty plot, and now I'm going to draw the circle. The definition of a manifold is that locally, that is, near any point on the manifold, it's a function graph. Either I can graph y as a function of x, or x as a function of y. And if we look at the top of the circle, where y equals 1 and x equals 0, you can see that y is a smooth function of x. So let's graph this. Instead of using the curve function, I'm actually going to set up a sequence of x values going from minus 0.8 to 0.8 and calculate the corresponding y values by taking the square root of 1 minus x squared. Remember, when x is a vector, y is just another vector where each component of y is calculated from the corresponding component of x. So now I plot the resulting points from these sequences of x and y values, and in red you see the top of the circle. Now if I go down to y equals -1, let's get that right, y is again a function of x, but it's a different function. Now I have to take the negative square root of 1 minus x squared. I do exactly the same thing, plot the result in orange, and we've got more of the circle. But we can't get the whole circle by graphing x as a function of y. So let's go over to x equals 1, y equals 0 on the right-hand side, get a sequence of y values that will fill in from minus 0.6 to 0.6, and calculate the corresponding x values with the smooth function square root of 1 minus y squared. Again, I plot the sequence of points, this time in blue, and we're almost there. I just have to fill in the left half by doing the same thing near x equals -1, and presto, we've got the whole circle. So there's the good news and the bad news about manifolds. Locally, a manifold is just described by a function graph. That's the good news. But the bad news is you frequently need to change active and passive variables near different points in order to get the complete function graph. So for this simple little circle, we needed 4 separate function graphs. Once we've got the manifold, we can calculate the tangent space very easily. It's just the graph of the derivative of the function that describes the manifold. I put some crossing dashed lines to show where I want to know the tangent space. I take my function f, y was the square root of 1 minus x squared, and I compute its derivative, and the function that I want to graph is 0.8, the value of y at the point where the dashed lines cross, plus the derivative evaluated at that point multiplied by x minus 0.6. And when I graph that using the curve function, you can see the dashed red line. That is the tangent line to the manifold. When I talk about the tangent space, I think of the origin as fixed at the point where those dashed black lines cross, and therefore this is just the set of multiples of a certain direction vector heading away from the origin. Now there, we wrote x as a function of y. But near this particular point, I can also describe the manifold by specifying x as a function of y. I do exactly the same thing. I graph the tangent line. Watch carefully. I didn't set the line type equal to 2. I get exactly the same tangent line, the same tangent space as before. Now let me show you how to get the entire circle in one fell swoop by using a parameterization. Clear my plot out, and I'm going to run a parameter, which I'll call t, in small steps from 0 to 2 pi. The x values will be given by the cosine of the t value, the y values by the sine. And when I plot those sequences of points, I get the entire circle. That's the great thing about parameterizations. In fact, ordinarily you don't use a parameterization unless it will give you the entire manifold. How would I get the tangent space here? Well, the tangent space was the graph of the function that specified passive variables in terms of active, but it's the image of the derivative of the parameterization function. Remember, the derivative is just represented by a matrix. A matrix has an image, the space that's spanned by its columns. I need the parameter value that will give us the same point where I plotted the tangent line before. Let me mark that point, and now let me define our parameter function. It produces a two-component vector whose components are cosine t and sine t, and I can ask for its Jacobian. When I look at that, I get a direction vector. Now let me plot the image of that matrix. All I have to do is plot a line where I take the crossing point of the black dashed lines and add on multiples of that direction vector. Here's a sequence of t values to multiply it by, and here's the resulting sequence of points. I've got the tangent line again. But of course I still haven't used the most familiar way of describing a circle. It's the locus of x squared plus y squared minus 1 equals 0. In order to look at that, we want to plot a contour line, and here's a very efficient way of doing it that I discovered on the internet. Both for x and y, I'll use a sequence of points running from minus 1.1 to plus 1.1. Way back when, we used outer to generate a table of multiplication facts for a finite field. What outer does is to take a sequence of x values, a sequence of y values, and apply a certain function, which in this case is going to be the function f, to each pair. So that's what happens when I apply z, and if I ask for a little bit of z, I see I've got a gigantic matrix, which you may recall is what the contour function requires. So I ask to plot the contour lines, but the only level that I want is the contour line for level 0, and there's the circle. Let's go back to the point where we want the tangent space. In order to calculate the derivative of f automatically, I need to write it as a function of a vector. So I replace x by v sub 1 and so on. And I ask for the Jacobian, which gives me a matrix with 1 row and 2 columns. There it is. There's the place that we want the tangent line. And you may recall the tangent space was the graph of the local function that specifies the manifold. It was the image of the derivative of the parameterization function. It is the kernel of the derivative of the function capital F in this case. Using the Hubbard's notation, I will say y dot, the change in y from our chosen point, is the active variable, and then the implicit function theorem specifies x dot. It's minus a inverse b times y dot. So I can work out the slope just by taking the ratio of components of the Jacobian matrix, specify some values for y dot, calculate the corresponding sequence of values for x dot, plot them up. I see exactly the same tangent space, exactly the same tangent line. Now let's look at some interesting examples from the textbook. Here's one where there is a very complicated looking polynomial function of x and y. And the question is, does this always, when graphed, lead to a smooth manifold? Here's how we find out. We define a function of x and y. There it is. And the test is that its Jacobian matrix is always onto, which means, put more simply, it never has components which are all 0. If it did, then the columns would span a zero-dimensional vector space. I can work out the partial derivatives by rules of elementary calculus. There's the first partial derivative plotted. There's the second partial derivative plotted. There is a line at the value 0, and you can see there's no place that both those derivatives are simultaneously 0, so we can conclude that the locus of points that satisfy the equation f equals 0 is a smooth curve. We don't have a clue what it looks like, though. In order to figure out what it looks like, I can set it equal to various constant values and plot the contour lines in a manner as described as before. And if I look at them, I say, yep, they are all smooth curves. The derivatives did not lie. Here's a slightly more interesting example. X to the fourth plus y to the fourth plus x squared minus y squared equals a constant. I'll define that function. I will look at its partial derivatives, graph them both, and now I see that the first partial derivative is 0 when x equals 0, and the second partial derivative is 0 both at x equals 0 and at x equals 1 over the square root of 2. So I now have three pairs of values. I could have had minus 1 over the square root of 2 also, where both partial derivatives are simultaneously 0, and I won't get a smooth manifold. Let's first try 0, 0. The function evaluates to 0, so the contour line for 0 is not going to give me a smooth manifold. If I put in plus or minus 1 over the square root of 2, I discover there's a problem at minus 0.25, and we can see what's happening by plotting the contour lines. So, there are lots and lots of contour lines, and you can see already something funny is happening with the contour line for the value 0. It appears to cross itself, and at the point where it crosses itself, I can't express x as a function of y. I can't express y as a function of x. We still didn't see what's going on for the negative values, so I will ask for a variety of negative values for the contour line. Now you see that in most cases I get a manifold. It's a pair of curves. It's disconnected, but that's no problem. Lots of manifolds are not connected manifolds. But as c approaches 0.25, these curves degenerate into a pair of isolated points, which don't get shown, but they're in the middle of that circle for minus 0.24. That's not a one-dimensional manifold. It's a zero-dimensional manifold. Next topic. Let's try parametrizing a manifold. In that case, the derivative of the parametrization function must be 1 to 1. It's got no way of being onto, but we can ask that it's 1 to 1, and the only way to fail that test is if it's the 0 vector. So here is a manifold that I cooked up. I parametrized x is t plus e to the t, y equals t plus e to the 2t. I calculate the derivatives. I plot the first one. I plot the second one. I plot the value of 0. And not only are the two components never simultaneously 0, neither of them is ever 0. That means that when I plot the manifold specified by this parameterization function, I expect to see a nice smooth parametrized curve. And sure enough, it looks very nice. We can find its tangent line if we want, say at a point 1.5. I calculate the x and y values there. So I can show the point that we're looking at. And when I calculate the derivatives, I get the two components of the derivative of the parameterization function. The rule is the tangent space is just the image of the derivative of the parameterization function. It is the subspace with a direction vector specified by those two derivatives. I can plot that easily by calculating its slope. And if I want to show the tangent line, I need to figure out what its y-intercept is, subtracting off the slope minus the x value. Once I have both the slope and the intercept, AB line will give me the tangent line, and there it is. A curious feature of this sort of parameterized manifold is that while I had no trouble generating lots of points on it, it's very hard to test whether a given point lies on the curve. If you look at the graph, you say, it looks as though x equals 4, y equals 10 may be on the curve. Well, I'm close, but I missed. And even if you find a point that's on the curve, you still need to use Newton's method to figure out the parameter value that goes along with that point. Now I'm going to make some small changes to these functions so that it fails the one-to-one test. I put some minus signs into my functions g1 and g2. Those persist in the derivative, and when I graph these two derivatives, I've cooked things up so that when the parameter equals 0, both the derivatives are 0. So when the parameter value is 0, the derivative of the parameterization function is the 0 vector, and that's a linear transformation that is not one-to-one because it takes absolutely anything into 0. So we expect to see problems now with the curve that's represented by this. There's a sequence of parameter values ranging from -3 to 2. I'll set up an empty plot and plot the points. And you see what happens. Now we get something that's not a smooth curve. It's got a little corner in it. We can zero in on the point where we've got trouble by using parameter values just from -1.6 to 0. And if I plot in one color the points for parameters less than that value, in a different color the points for values greater than that, you can see what happens. If you think of this as a moving particle, what it does is it comes in along the red line, it comes to a stop, and then it turns around and heads off into a different direction. Right where it changes direction, we don't have a smooth manifold. That's not the only way we can start with nice smooth-looking functions and fail to get a smooth manifold. Here's a classic example where x equals sine t, y equals sine 2t. I run the parameter from 0 to 2 pi, and when I plot this, I get something that looks like a bow tie. The problem here is that the parameterization function is not one-to-one. There are multiple values of the parameter that lead to that same point on the manifold where it crosses itself, and as a result we can neither specify x as a function of y nor y as a function of x. Final example is a two-dimensional manifold in R2. That has to be just an open set, and if you talk about it as a function graph or as a locus, there's nothing really interesting to say about it. But if you talk about it as something that can be parameterized, it does get interesting. This example is actually from chapter 2 of the textbook, and I'm putting a slightly different interpretation on it. So let's set up an empty plot and set up the problem. We start with one circle of radius 3, another circle of radius 1, and the rule for generating the manifold is pick any segment joining a point on the left circle to a point on the right circle. Take the midpoint of that segment and you get a point on the manifold. So I will generate a pair of random angles, theta and phi, and I will plot the segment that runs from the point generated on the left circle to the point generated on the right circle, and I will show you its midpoint. Now that doesn't tell us much about the manifold, but R is happy to plot lots and lots of randomly selected points. Let's do 1,000 of them. I generate 2 random angles. I generate a point on the manifold. And now it's clear what's going on. The manifold itself is the annular region in between the 2 circles. Now the interesting question is, does that region between the 2 circles include the circles themselves? And we can answer that question by using the one-to-one test for the parameterization. There's my parameterization function written as a function of a vector. That's the angle for the first circle and the angle for the second circle. And let's look at what happens when those 2 angles happen to be equal. I've given both the same value, 1 radian. There is a segment. There is the midpoint, and you can see it's right on the boundary of the manifold. If I calculate the Jacobian matrix there and form its derivative, its determinant, the determinant's 0. This matrix is not invertible. That means that the matrix is not one-to-one. It fails the test, so that particular point is not on the manifold. There's another way for this to happen. I pick another arbitrary angle, 2.5 radians, and this time I will consider the case where the 2 angles differ by 180 degrees by pi radians. Again, if you look at blue, you now may be able to see that the midpoint is on the inner circle. Again, the Jacobian matrix is not invertible. So we've concluded whenever we've got a point on the boundary of the region, the derivative is not one-to-one. That means that can't be a point on the manifold. We have to exclude those boundary points, and the manifold, the region between the circles, is an open set. Now, one last weirdest yet example, a zero-dimensional manifold in R2. As a function graph, this is uninteresting. As a parameterized manifold, this is uninteresting. But as a locus, it's kind of interesting. So here's a function of x and y, x squared times x minus 1 squared plus y squared times y minus 1 squared. I can plot contour lines for this, and you can see what's happening. Those are closing in on 4 points where x and y may be either 0 or 1. So the equation f of x and y equals 0 defines a manifold all right, but it's a zero-dimensional manifold consisting simply of 4 isolated points. Let's try our derivative test on this. I rewrite it as a vector function, so I can take the derivative automatically. I pick one of the points, I evaluate the Jacobian there, and round it off. Both components are 0. It fails the onto test. And for each of the 4 points it will. That's why we get a zero-dimensional manifold. Changing this slightly, I get a new function, x times x minus 1 times y minus 1. This function is now going to be 0 when either x or y is 0 or 1. And if I plot contour lines for this, I see that the contour line for 0 consists of a pair of horizontal lines crossing a pair of vertical lines. Where the lines cross, we can't have a point on the manifold because x isn't a function of y isn't a function of x. So again, f of x and y does not define a smooth one-dimensional manifold. If I rewrite it as a vector function and choose to evaluate the derivative where the contour lines cross, again, I see that the derivative fails the onto test. If I want to make this into a manifold, what I do is eliminate those 4 points. That disconnects the manifold, but it is then the sort of proper one-dimensional manifold that you would expect to see if you impose a single constraint in 2 dimensions.